Maybe you should have advertised a bit more. But yeah, tēnā koutou, greetings to all. My name's James, and I'm a climate risk scientist at NIWA, which is the National Institute of Water and Atmospheric Research in New Zealand, but more commonly known as NIWA. So yeah, fortunate to be all this way across the world to present to you on some work that we do at NIWA that I've been involved in for the last few years. It's a project that's shared with SPC, the Pacific community, who are based in the Pacific, and it's themed on enhancing resilience to pluvial flooding in Pacific Island nations. And it's a novel approach to rapid rain-on-grid modelling and risk assessment using some open source softwares that we've developed called BG Flood and Riscape. So a bit about NIWA. We're a Crown Research Institute, which means we are largely government funded, but we also have private funding sources. We work mainly in the Australasian region, the Pacific, Australia and Antarctica, but also around the world sometimes, and our focus is freshwater, climate and marine science. And there's a few links to our website and Instagram if you want to check it out more. As part of the project, we had a use case called Use Case 2, which was focused on tropical cyclones and post-disaster needs assessment. And the main tasks of Use Case 2 were creating national risk models and hazard maps, which would detail tropical cyclone and flood inundation and exposure. And they were intended for use in pre-event and post-disaster needs assessments and to help build resilience to these disasters within the community. So a large part of my focus was creating national flood maps for Samoa, which, to those of you that are unfamiliar, Samoa is an island nation in the South Pacific. It consists of the two main islands, so you have Savaii and Upolu, and that's a picture of its main capital, Apia, which is where most of its population is focused. And it tends to experience high rainfall, about 3,000 millimetres per year, and it is also very prone to the cyclone events. So here's just some images of flooding in Samoa. You can see it's pretty destructive. That's one of the main streets in Apia that's almost fully inundated there after an event. And I'll touch on last year in February, New Zealand also experienced our first major cyclone in many years, so Cyclone Gabrielle, which hit our sort of Hawke's Bay region over here in Gisborne the most, caused mass flooding, flood depths almost over 4 metres, which almost completely topped some houses. And as bad as this was, it prompted more funding to be directed into hazard and risk modelling in New Zealand, which was able to be fed into the Pacific as well, just to help better prepare our country and the countries we work in for these events. So the modelling method we have used in this study is commonly known as rain-on-grid. Rain-on-grid's actually been around for some time, but it's recently been more talked about as a useful way to create indicative flood maps. So these flood maps are just intended to inform decision-making processes. They're not really intended for use in engineering design as such. You wouldn't want to use them to build a bridge or a culvert. But the benefit is it relies on sort of limited data to be performed, which in the Pacific, that's a huge advantage where there's big data challenges and access challenges as well. High-resolution LiDAR is only available in very few places. So it can be quite a challenge to sort of figure out how we can make the best models we can using these limited data sets we have available. So the software we use to do this is called BG Flood. So BG Flood is a shallow water equation, SWE model, which is built upon the same finite formulation and adapted to a block tree structure for the GPU. But it's designed to simulate inundations caused by rainfall, tsunamis, tides, storm surge, and can also run these all in combination. And there's the GitHub link to it there if you want to check it out for yourself. It's hosted by on the creator's name, Cyprian Bossarelli. He's a good friend of mine, and him and a few others have coded this up from the ground based on some other models. So this is a flow diagram just to show the basic rain-on-grid modelling process that we use. the inputs for rainfall or river flows are just set up as CSV or text files. And other inputs can be set up as raster layers, and they're all just held in a central folder together, as well as a text file which has the model's main configuration on it. It doesn't have a GUI, it doesn't have an interface, but it's run pretty simply just through the command line. Once you have this sort of folder set up with the main files, you can simply just prompt it or call the model to run on the command line, and you're away. So the modelling process utilises spatial data to produce spatial data. I believe you don't necessarily need to be a hydrodynamics engineer to run this model to achieve it. I'm an environmental scientist myself, and yeah, it's a great way to just produce indicative flood maps that have a bit more detail than regular extent flood maps that you could produce in other GIS softwares. From the output of this model, we can get net-CDF files that also have a time variable to them, and they have depth and velocity and a few other factors. This is just a spatial representation. Oh, it's pretty blurry up there, but of a model configuration, which this is in QGIS, which QGIS isn't vital to running a model. I think most of the layers we use were created just using Python scripts, but it's a good tool to help us just spatially view the model and understand sort of what's going on, make sure everything's kind of looking right. The white box you can kind of see there would be our model's high resolution area, so that's where we'd tell the grid to adapt. You could go down to a level of 5 or 10 metres where you're most interested to see the flood impacts, but outside of that area you might only want to run the model to say 20 or 50 metres, and that all impacts the model's runtime obviously and size of the data that it produces. So here's the DEM layers we've used in the study. The top one, the green to brown layer, is a 5 metre composite DEM. So this is also created by NIWA, where we used LiDAR in the areas of Samoa where it existed around Apia and a few other spots, and then combine that with the FAB DEM. So this again was achieved in Jupyter Notebook using a script, and it helps us be able to run the model on national scale. Generally the LiDAR exists in the main model areas that we're concerned with anyway. So where the 50 metre DEM exists, we're not too worried about those areas. There tends to be less population. And then another important aspect that went into it was the floodplain delineation. So this was another process that we created where we were able to sort of detect floodplain areas, combining a few different factors like slope, elevation and proximity to rivers. And those floodplain areas just help us. We input that into the model to tell it where to run those high resolution areas, as they tend to be the areas of most concern. This is just an example of what the rainfall input looks like. So you do need a temporal rainfall input. For this study, we use depth, duration, frequency values that were developed by NIWA as well. This one is for Apia Samoa for a specific station. You can just use a temporal rainfall input if you have an event of historic rainfall data. Obviously, rainfall data can be a huge access issue, as it doesn't tend to be open a lot of the time, but that is needed for the model. So here's some examples of output. So this was for a catchment study we did for the Vasigano catchment, which flows, this is the Vasigano River, flows all the way into Apia. And it's a pretty looking map. And generally, so we validated this by checking it against some high resolution modelling that was done in the area, just to validate the extent of the model. The Vasigano is generally, it's been more researched because the Vasigano River tends to flood so much. There's been more work done in the area. And when we checked it against that, we're generally happy with the main extent of the model. There still can be some potential unnatural pooling as we don't incorporate culverts or other stormwater systems into the model. But again, for decision support, it's a pretty good way. So this is for a 2-hour duration storm for a 10-year ARI. The next one's a 50-year and 100 year. So generally we can see as we flick through them, the flooding depths increasing. And this is a maximum flood depth map too, so it's an output TIFF file of the maximum flood depth that occurred at every cell throughout the model. We're also in GIS able to extract points from our output layers that just help us to understand the water depth or the peak time of flooding. So for this catchment, it's quite a short, steep catchment. So the peak time of flooding is generally faster and occurs around the 2 to 4 hour mark. But obviously in lower, larger catchments, that can be slower. And that just helps us to further inform the risk later on in RISCape and the decisions later on too. So once we had tested our model in the Vasigano catchment, we next adapted it to national scale. So here's the Savai'i national scale map. For an island country, rain on grid modelling works really well. At national scales, we can distribute the rainfall across the entire country in one singular model, which takes only a few hours to run, depending on the resolutions that you specify. Countries with multiple islands like Vanuatu can be more challenging because their islands are spread further apart and the rainfall bands tend to be quite different, but Samoa is generally the same. For this national scale map, we used the worst rainfall depth table that we had possible, just to make sure we're getting the worst possible example. And here's Upolu. When we zoomed into this map, back on the Vasigano catchment, the extent of the flooding was pretty similar to our catchment focus study, and we're pretty happy with the results. They're potentially better as the national scale map allowed for more combination of flow between catchments and gullies. So the next part of the process involves quantifying exposure and loss metrics and using RISCape. So RISCape's an open source multi-hazard impact assessment tool that was developed by NIWA and GNS Science in New Zealand. So GNS are our Crown Research Institute for Earthquakes and Geology. So what RISCape does can be replicated in GIS and other coding solutions, but the benefit of it is that the engine's purpose-built and optimized to perform the functions, so it can perform national scale models relatively quickly to what maybe a GIS program could. And it's more user-friendly. It now has a GUI that's been created that allows non-GIS users to also perform risk models, input their own data, and it also, there are a few microsites we've developed for the Pacific Islands that also allow non-GIS users to view the data easily. So in the Pacific, as part of this project, we did go in and train these countries on QGIS and other programs to hope that we can allow them to continue that capacity after the project's finished. But obviously this isn't always the case and it's not always adopted. So RISCape was a handy solution to make sure that they can actually make use of the data that we're creating. So here's some visual examples of RISCape. The engine has its own language, but it's similar to Python and it's run from the command line. The project part is an online cloud service that can hold models and data. The RISCape platform, as I mentioned, is used by non-GIS users to set up and run models with a GUI. And again, for certain countries, we had RISCape microsites, which just help to easily view the model's outputs. And there's a link to it down there if you want to check it out. It's got heaps of tutorials and documentation available for learning. Here's an example of the RISCape platform. So this example, I believe, is for Cyclone Judy. So over the side here, they've got some wind bands, some regional areas. There's a few different aspects of drop-downs that they can input. They can input their own custom data to the side and simply click Run the Model, and the RISCape engine will start to run. RISCape can run scenario and probabilistic models. So a basic scenario model is the hazard and the exposures, so that could be roads or building footprints. We can combine the two to generate the hazard exposure of that and further the impact. Dependent on the data quality of your exposure data set, whether it has, say, for building footprints, it could have a floor height or a wall material. Then if it has more data, we can start to build in vulnerability functions that work with the hazard and the starter to produce, say, a monetary loss or more vulnerability figures. And then a probabilistic model is similar, but you can incorporate more hazard layers, and RISCape can run through them all simultaneously. So again, this is just an example of RISCape's function. Just like in GIS processes, you can identify buildings exposed, assign risk levels. This is based off the water depth at those points. And then we could produce a vulnerability function that has a monetary loss based off the building type. Here's an example of another dashboard that was developed for Vanuatu. So this was at an early stage where we had only modelled in Port Vila and Luganville up the top there. And we gave this dashboard to Vanuatu, or created it for them for easy use to look at the pre-computed flood maps we had done. So we computed flood maps for several different scenarios, which were held in this dashboard. They can easily call upon the scenario that they're after, or the region, and that will, the risk is already pre-computed in RISCape as well, the exposure results, and this dashboard will just pull that all up on a nice interface for them to view easily. I'd like to mention that in Westport, New Zealand, this has been done at a slightly higher level as well, where NIWA's just developed a way to match our long-range forecasts. Westport's a region on our west coast that gets hammered with large rainfall events quite often as well, and we now have this way that looks at the long-range forecasts for sea level and river flow, and there's a whole library that's been developed of pre-computed flood maps. The machine learning algorithm will view those forecasts, pull out the flood map that's most similar or fits the forecast best, can run that through RISCape, and even in hours building up to an event, we can start to quantify what the potential losses or damages of that event are going to be. Final remarks, I'd just like to thank a few others who played big parts in this research and this study, and there's some more links to the open source software that was used. I didn't mention HECRAS, as that's a whole other thing to get into, but that's also very useful. I think that's me, so Kainui, Tēnā, Mo te Niwa, which means that's enough for now. Thank you.